Stars are just bright points in the sky, without extension and without any dimension we can see with telescopes. Then astronomers have to find from this bright point all the information they need to tell how big is the star, how hot is the star, where is exactly that star. The first important task is to tell where is a star, so the distance to a star. The main problem is that we cannot use traditional techniques such as the radar. We need to find another solution. This solution has something to do with our eyes. Now put your finger right in front of you, say one palm from your nose. Then alternatively close one eye and the other eye. What you will see is that your finger is actually moving with respect to the screen you're looking at. When you close one eye, your finger probably appeared here. When you close the other eye, your finger appeared to be here. This is what we call perspective, but astronomers use another word, which is the parallax, which has something to do with the two different points of view we have with our eyes. Now try to do the same thing with your finger a bit farther away. Close the right eye, close the left eye, and see what happens. If everything was right, now you should have seen that in this case your finger moved not a lot. The first case probably here, the second case probably there. This means that the parallax has something to do with the distance. Your finger was closer when the change in position was larger. Your finger was farther where the change in position was smaller. Now, how can we use this effect with far stars? They are so far that we cannot use our two eyes. We have to use another sort of eye. And this eye is provided by our planet, the Earth. The Earth rotates around the Sun. And each 6 months, it moves from here to there, corresponding to the two eyes we will see to look at the finger or the star. Now what happens? That a star appears to be in one point at a given date and then into another point at another date. The angle of apparent motion is called parallax. This angle depends only on the distance to the star, and of course if the star is too far for this effect to be visible, we cannot use this parallax. Once you have the angle, with the help of trigonometry, you can tell how far is the object. To be more precise, when you look at the star, then you wait 6 months to look again at that star. You take the apparent motion of this star. So the larger this motion, the closer the object. The tighter this motion, the farther the object. Of course, if the object has no motion, this means that it is too far to be seen with the parallax. The Earth is exactly the two eyes 6 months apart, and distance I knows is just one astronomical unit, which we call baseline. When you do all the calculations, it turns out that for a single arc second, which is 1/3600 of a degree, so it's a very tiny fraction of a degree. So this change in position corresponds to a unit that we call parsec. 1 parsec corresponds to around 3 light years. Then the closest star we have, which is Proxima Centauri, which is at around 3-4 light years, lies exactly at around 1 parsec in distance. In other words, during 1 year, during 6 months, we see this star here and then here, and the distance we measure as an angle is just an arc second, which is a tiny fraction of an angle, as I said before. Once we have the distance to a star, we can use the fact that the farther is a star, the dimmer it should be. In principle, if you have the same star close to your eye, and then you look at the same star a bit farther, the same light should look dimmer. It's perfectly reasonable. In physics, this corresponds to a very precise law, the inverse square law. In other words, the farther you go, and the dimmer it will be with a precise pattern. This means that a star that is twice as far will be 4 times dimmer, while a star which is 3 times farther will be 9 times dimmer. On the other hand, when we have the brightness of a star, we can exactly know where is that star by just telling the difference in brightness and using the square root. This is particularly useful when we cannot determine the distance with the help of parallax, and we just can use the intrinsic luminosity of a star, where intrinsic means the own luminosity of a star, not the apparent, so what we see. Astronomers use a word to tell the brightness of a star, and this word is magnitude. For historical reasons, the magnitude is very strange. When it was set, the magnitude number 1 was the brightest star visible in the sky, while magnitude number 6 was the faintest naked eye star. Then we have found that there are stars a bit brighter, and we needed a more precise tool, which is not just look with the eyes. And for this reason, now we have this strange scale, which goes from very faint, which is 25 magnitudes, to very bright, which is our sun, which is negative 27. It's a bit counterintuitive, but you can understand it in this way. If you go from magnitude 0, which is Vega in this picture, to magnitude 5, you have an object which is 100 times dimmer. Here the keyword is apparent brightness. This is what a star looks like. But we are interested in the intrinsic luminosity, so the own luminosity of a star. And what we can do to obtain the intrinsic luminosity, so the own luminosity of a star. We pick up the star and we bring it to 10 parsecs, and we look at it now. Of course, this is an ideal process. We have to do with formulas. In this slide, we can compare the apparent magnitude and the absolute magnitude. And it's clear that the sun is not as bright as we can imagine with a magnitude which is 4.8. And compared with Arcturus, it's much fainter. On the right, we see the visual luminosity, which compares directly what we see in the sky with the intrinsic luminosity. Well, now we understand that if we know exactly the intrinsic luminosity of a star, we can easily tell how far it is. So having another technique, compared with parallax, to tell how far is a star. Astronomers always look for independent way of measuring some property of a star. We know that stars walk almost precisely as a black body. And fortunately, we have a very precise law connecting the temperature of a black body and the luminosity. This goes as the fourth power of the temperature. Namely, if we have an object which is twice as hot, it will be 2 to the fourth power, so 16 times brighter. Here we have to pay attention to the details, because the star can be large or small, and this will affect the luminosity. Well, again, the physics provides us a very precise law, which goes as the square of radius. Namely, if an object has a radius which is twice as large, it would be 4 times brighter. This causes some difficulty because we can have a large red star with the same luminosity as a medium yellow star with the same luminosity as a bright blue small star. But once again, the physics of black bodies helps us. A hot star will emit more in the blue side of the spectrum, while a cool star will emit more in the red side of the spectrum. In other words, the color of a star will soon tell us what is the surface temperature. Once we have the surface temperature, we can obtain the intrinsic luminosity, and once we have the intrinsic luminosity, we can get back to the distance to that star. As we have seen in a previous class, we can use the absorption lines in spectra to tell also what is the composition of a star. Here we have Vega and Deneb showing components of iron. While looking at the stars carefully, we also perceive that they have a proper motion. Namely, they move year after year. This motion is very, very difficult to see because these objects are very far from us. And despite that, with the help of geometry, we can tell how far and how fast they are moving. For example, with the help of Doppler shift, you can tell whether they are moving away with a red shift or closer with a blue shift. And with the help of geometric properties, so by looking at them year after year, so one year they are here, the next year they are here, and so on, we can also tell what is the displacement in this direction. We combine the two motions to have the overall direction of a star. The hardest task is to measure the mass of a star. We can't do that for lonely stars. We need a couple of stars rotating around each other in order to exploit the Kepler's third law. A couple of stars rotating around each other is called a binary star. A spectroscopic binary is a couple of stars showing lines moving time after time, blue shift, red shift, showing that there is a rotation around each other. There is also a particular class of stars which are called the eclipsing binary stars, which we are looking by a good side, and they are eclipsing each other while rotating around each other. So this causes a sudden reduction in the luminosity of that group of stars, and this decrease in luminosity time depends on the relative sizes of the two objects and on the velocity of rotation. So when we have eclipsing binaries, we can measure the size of stars. Recent techniques allow us to measure the size of a star even for single stars. This technique uses the variation of luminosity as a function of time, which strictly depends on the star size. In this lecture, we have learned how to measure the principal properties of a star, including brightness, luminosity, color, temperature, size, and distance and mass.